So in this screencast, we're going to look at the chemistry of alkynes, where we start off looking at the synthesis of internal alkynes from terminal alkynes, and then we're going to transition into alkyne addition reactions, where we're adding electrophiles to the triple bond of the alkyne. So let's start off with examining the formation of a carbanion from a terminal alkyne. So if we consider the molecule propyne, and we know that the pKa of this sp hybridized carbon H bond is 25. We know that if we treat that with a strong base, we can deprotonate that to form a carbanion. So what is a typical strong base that is used? So something like sodium hydride in a solvent of THF, which is tetrahydrofuran. So this is a cyclic ether. And that's going to affect an acid-base reaction to generate the negatively charged sp hybridized carbon. So this is a carbanion. So I'm just going to put a bracket around this because we're forming that in solution. A carbanion, as we've seen, is a nucleophile. So again, it has the lone pair of electrons on carbon. We know carbon likes to be neutral, so when it's negatively charged, it's going to be a pretty strong nucleophile. And so we can react that with an electrophile in an SN2 reaction. So what I'm going to do is put this semicolon here. That means after we form the carbanion, we can add an electrophile. So say we're adding methyl iodide as our electrophile. We know the iodide's delta minus, the carbon's delta plus. And so this is just going to do an SN2 reaction that we've seen in the prior chapter. So the nucleophile attacks the electrophile. The leaving group leaves, so SN2 mechanism. And now we are transforming our original terminal alkyne into an internal alkyne. So now we've formed 2-butyne. And so again, an internal alkyne has the sp hybridized carbons each bonded to a carbon. The terminal alkyne, you have this acidic CH bond. So that's a pretty straightforward process. Let's look at, we saw this term prior, retrosynthesis. So retrosynthesis of an internal alkyne. So this is where we really develop the chemical intuition about reactions. So say we were given this molecule, 4-methyl-2-hexyne, and we want to convert that to the structure. So let's go ahead and draw our carbon chain. So CH3, there's carbon 2, there's the triple bond, so that's the 2-hexyne part. So we have C, 1, 2, 3, 4, 5, 6. Let's put our numbers in to help us here. 1, 2, 3, 4, 5, 6. We see that carbon 4 has a methyl group, CH3, and then we'll just plug the rest of our hydrogens in here, H2, H3. So we've converted this name to this structure. Now we can look at this internal alkyne and we can devise two methods on how to synthesize that. And so this is called retrosynthesis. And the reason this is important is because molecules can get pretty complex, and we want to break them down into very simple starting materials called feedstocks. And this particular example, we can cleave with a dotted line. So I want to say we can cleave here between carbons 1 and 2. And our arrow, this is a retrosynthetic arrow. Again, we're thinking sort of in reverse engineering. We know that the sp hybridized carbon of the triple bond can be negatively charged. So that's the nucleophilic component. And then we see the one position carbon, it just ends up being one carbon, CH3. Now if we were matching polarity, this would have to be some sort of plus. We know we can't just have a floating methyl group as a carbocation. So in reality, we're matching the polarity. This is the nucleophile, this is the electrophile. But what do we really need to start with? So we could say this could come from iodomethane, and then this would come from the terminal alkyne. In this case, let's put the numbers in there so we can name this correct. 1, 2, 3, 4, 5. This would be 3-methyl-1 pentyne and iodomethane. So as we saw above, we can take this terminal alkyne, deprotonate it, and then add in this electrophile. So the carbanion attacks the electrophilic carbon. We form that bond, and then we end up with the desired product. So the other route, the other pair of nucleophile electrophile, if we cleave this bond, we would end up with the following pair. So CH3 negative. Now we have CH3 plus. Again, we're just thinking in terms of matching the polarity of the reaction. So if we had to transform these into actual things we would use, we could start with propyne. And if we number these things here, 1, 2, 3, 4, we could say ICH. So that would be 2-iodobutane. And so as we saw above, the reaction proceeds through an SN2. So if we consider the electrophiles, here we have a methyl electrophile, iodomethane. Here we have 2-iodobutane, so this is a secondary alkyl halide. So you could possibly argue that this pair might be better for the SN2 because you have your strong nucleophile, you have a less sterically hindered electrophile, so that would be a good SN2 reaction. Here you're increasing some bulk, you have a secondary electrophile now. Remember the rate for SN2. So this might be less advantageous based on the rate of the nucleophile attacking the electrophile. But practically speaking, in an industrial sense, you'd have to, if you were a chemist working on this, you would get with people that source these different materials, look at what the cost of each of these is, and ultimately make your decision on cost. So thinking about things in different fashions is good, because it gives you the chemical intuition about how these molecules are made. So a common addition reaction to alkynes is hydrogenation. So we know that by visually inspecting an alkyne, we have sp and sp hybridized carbons that are bonded together using a sigma and 2 pi bonds. So we have 2 degrees of unsaturation. And we're going to treat that with excess hydrogen gas in the presence of a precious metal. So a transition metal such as palladium, platinum, or nickel. So these are catalysts. And then the solvent, which is typically an alcohol, so a polar protic solvent. And so what that's going to do is add 2 equivalents. So we have 2 degrees of unsaturation. We have excess hydrogen gas. We're adding 1 equivalent of H2 and then a second equivalent. And now we're fully reducing that triple bond down to the sigma bond. So this is going to end up as the alkane functional group. And now you notice we have no degrees of unsaturation left amongst that initial triple bond. So some examples of this. If we were starting with 1 butene and we treated that with excess H2 gas, platinum metal, and ethanol. So again, this is a hydrogenation. We're completely reducing down the triple bond, so we would end up with butane. So again, I'm presenting it with just the words so that hopefully you develop the intuition to visualize what this is in your mind. 1 butene that has an alkyne. We're treating with hydrogen gas, platinum metal catalyst, and polar protic solvent. So we're doing an alkyne hydrogenation. That's going to get us butane. So an alternative set of conditions that's hydrogenation, but does not reduce fully down to the alkane, but reduces to the alkene, uses a different type of catalyst. So let's look at an example of that. Say we're starting with we're going to start with 2-hexyne. We're going to treat with that with hydrogen gas, palladium metal. So we saw the transition metal above, either platinum, palladium, or nickel. So if we have palladium metal in the following conditions, so I'm going to use barium sulfate, and then this molecule as well, called quinoline. With methanol as our solvent. These conditions, even though some of the things are the same as above, the conditions with barium sulfate and quinoline act as a poison to the catalyst. So this prevents complete reduction of the alkyne to the alkane. So instead, it actually stops at the alkene, and specifically, it does a cis addition. So the alkyne ends up being the cis geometrical isomer. So here we would end up with cis 2 hexene. And so I want to stress the importance of this, because if you're really engaged in learning this material, you could look at, say, 2-hexyne. Do that example that we just did above about what are the two methods by which you could make this. So if you dissect here, you dissect here, you can think of those methods, how you would make this. Then you could deploy these conditions to take the alkyne to a cis alkene. And then if you think about all the alkene addition reactions that we learned in the prior chapter, you're really starting to put all these things together. So that's what organic chemists do, is they take feedstock materials from petroleum or plant-based sources, and they add value to them through these reaction sequences. So typically, at this point in the semester, when you're learning more reactions, it can get sort of overwhelming to understand them all in the context in which they're used. So one strategy you can take is to use colored note cards to make flashcards. So you can make homemade flashcards that show these different transformations on one side, the reagents on the other, or alternatively, you show the reagents and then you describe in words what's happening. So however you learn best. Also, there are many apps you can get that have these note cards already built into them as well. So in the prior example, we saw that with palladium metal in a catalyst such as barium sulfate and quinoline, you can do a hydrogenation of the alkyne to get the cis alkene, which is not further reduced to the alkane. So what if you wanted to make the trans alkene? So you'd have to use alternative conditions, and this is called the dissolving metal reduction. So think about that. That's sort of strange, right? Dissolving metal. How often do you see a metal dissolve in anything? Well, it turns out you can take an alkyne, as shown here, again, 1-2 degrees of unsaturation. Elemental sodium, that's what the little naught symbol means. So elemental sodium, this is typically purchased as little cubes, little silverish looking cubes stored in mineral oil. So if you take your alkyne and you dissolve it in ammonia, so liquid ammonia, ammonia is a gas at room temperature, but you can condense it at about -30 degrees. Reactions are typically run at -78 degrees. So you have liquid ammonia, your alkyne, and you throw in little chunks of elemental sodium. What will actually happen is an electron transfer process which reduces the alkyne to a trans alkene. So again, as we mentioned before, taking your feedstock chemicals, making an alkyne through SN2 chemistry, and then you can access different geometrical isomers of alkynes using either hydrogenation or dissolving metal. So this is a pretty interesting mechanism. So let's actually take a look at how you end up with the trans geometry. So it turns out when you take sodium metal, and you dissolve it in liquid ammonia, actually what's happening is an electron transfer process. So you have ammonia, and I'm gonna do a dot and show like a complex with an electron. and then you have your sodium cation. So basically the sodium is donating an electron, you're forming this complex here. And what's interesting about this is ammonia, when you condense it, is a colorless liquid. It's very pungent smelling, but it's a colorless liquid when you condense it. When you add in the sodium, you actually see the formation of a really deep blue color. I used to run a lot of these in graduate school, and I always found it really cool to watch that happen. So you can actually see as you throw the sodium in there, the sodium dissolves, and then you form this deep blue color, which is indicative of this this solvated electron. And so that's what plays a key role in this reduction process. So here is our alkyne. And I'm going to write the electron as E-. So at this point, the alkyne is acting as an acceptor of that electron. And we saw that when one electron flows, we use a single-headed arrow. So it's going to add to one of those carbons, and then we're going to break a pi bond with a polar mechanism where both electrons then move. And so if we consider that addition of the electron across a pi bond, it is at that stage where we actually form, so there's our single electron. We form this species, which is called a radical. So an unpaired electron with a negatively charged carbon. So this is a radical anion. So there's our negative charge that's conserved. And so we know that negatively charged carbons are good nucleophiles, or alternatively good bases. And so what that's going to do is abstract a proton from the ammonia. So we're drawing this geometry as trans, because if we drew it as cis, you'd have a negative charge next to an unpaired electron. That would be pretty severe repulsion. So what happens next is a proton transfer reaction. We have a base. We have ammonia, which is our acid. So we end up with H. And so we're in that process, we're losing the negatively charged conjugate base of ammonia. So we lose that, and then we're forming this radical. So a radical is an electron deficient carbon, obviously. So another equivalent of electron comes along to pair up. So here again we have a vinyl anion. It's important to remember that now the negatively charged resides inside an sp2 hybridized orbital, because the p orbital is taken up by that pi bond. So because this is an anion, we're going to do another proton transfer reaction. Again, we're losing an equivalent of that conjugate base. And we're ending up with our trans geometry. So again, we rationalize the trans geometry based on this initial addition that's happening here and that we want to maximize the distance between the negatively charged carbanion and the radical. So if we have them trans, we're minimizing that repulsion. We do a proton transfer at this carbanion. We then have this radical, another electron adds to form the vinyl anion, another proton transfer, and we end up with our trans alkene. So just as we saw with alkenes, we can add halogens across alkyne triple bonds. So a general reaction of that. So we have R1, our triple bond R2. So typically for halogens, we're using either chlorine or bromine. And we'll just say a solvent like dichloromethane. Again, that's a polar aprotic solvent. So it's there as the solvent to dissolve the starting materials and the reagents. So basically, we're going to add the halogen across the pi bond, and you can actually end up with a mixture of the cis and the trans. If you were to use excess, molecular halogens, you would actually do double addition. And so that essentially you would basically convert these initial cis-trans geometrical isomers. They would basically converge. Into a structure that would look like the following. So just a little bit of nomenclature that we use in organic. So a 1-2 relationship is called vicinal. So you're ending up with, we could describe a couple different things here. So this vicinal relationship, and the halogens on a single carbon, that would be a 1-1 relationship because they're both bonded to the same carbon. That's called geminal. And again, that's basically a relative thing. It's not really IUPAC. By relative, you're talking about two functional groups. So these two carbons are vicinal to one another. These two halogens would be geminal to one another. So these would be geminal. These halogens here would be vicinal. These would be vicinal. So that these are just ways of communicating where functional groups are relative to one another. So let's look at an example of that. If we were to start with this molecule, let's go ahead and figure out what the name here is. So 1, 2, 3, 4, 5. So we're starting with 1 pentyne. And say we're going to treat that with bromine. To begin with, we're just going to use 1 mole equivalent. So that what that means is 1 mole of this for 1 mole of this, so a 1-to-1 ratio. which essentially we're going to add the bromines across the triple bond, implying that we're going to end up with cis and trans geometrical isomers. So let's go ahead and draw those out. So there's our double bond, say H, Br, Br. So that would be the cis. And again, the way we determine cis or Z when we're using these nomenclature descriptors. So you're looking at each sp2 hybridized carbon of the alkene. So we're looking at this one first. We're comparing the substituents, so the atomic number. So bromine has a higher atomic number than hydrogen. So we would say this is 1. We go over to the other sp2 hybridized carbon. Bromine versus carbon. Bromine versus carbon. Bromine wins. This is 1. So the 1s are on the same face. So that equals cis or Z. So let's just go ahead and name this so we get practice doing that. 1, 2, 3, 4, 5. So it's a pentane chain. We have an alkene at the 1 position, so 1 pentene. We have 2 bromines, so we could say this is 1, 2, dibromo, 1 pentene. And then we can indicate the geometry at the front here by saying Z. So Z1, 2 dibromo, 1 pentene. So as I said before, we're also going to get the other geometrical isomer. So now you can see the 2 priority groups are on opposite faces. So that equals trans or E. So we have E dash 1, 2, dibromo 1 pentene. So you could assume that you're probably going to get more of the E or the trans just based on minimizing the steric clash between the 2 bromines. So if you were to take this product mixture, which would probably be very difficult to separate, and you treated that with another equivalent, so a second mole equivalent. So now we have the first one, here's the second one. Both of these are going to converge to the same product because we're adding now bromine across, bromine across. So again, here's our numbering, 1, 2, 3, 4, 5. Now we would number this 1, 1, 2, 2, tetrabromo, pentane. So when you're looking at these conditions, you have to identify where the alkyne is, how many equivalents of the halogen you're using to determine where it stops. Does it stop at the alkenes, or do you add a further equivalent and get the alkane? So in this next alkyne addition reaction, we're going to look at the addition of hydrogen halides. So we've seen these as acids, right? Hydrohalic acids, HCl, HBr, etc. to the alkyne. So I'm going to use this, the terminal alkyne as the example here to show that if we're adding 1 mole equivalent, it's going to follow Markovnikov's rule, where that basically states the carbon that has the most hydrogens gets the initial electrophile, in this case that being another hydrogen. So our choice here, the terminal carbon, which has the hydrogen, gets protonated. That's going to generate a carbocation there that is then trapped by the conjugate base of this acid. So the Markovnikov's rule explains the regiochemistry of this addition. Remember what regiochemistry means. We have the choice of these sp hybridized carbons, and then the choice of which one gets the H, which one gets the X. So this obeys Markovnikov's rule, and if we had another equivalent of HX, that would still further obey. Again, this is the carbon bearing the most hydrogens. It gets the hydrogen. We form a carbocation. It gets trapped by X. So we have a methyl group at the terminal now, and now look, we have this relationship which we saw before, this 1-1 relationship. That is a geminal relationship. So this is a geminal dihalide. So let's go ahead and look at a specific example of this. So say we're starting with one pentyne. And I'm using the terminal alkyne because it shows the chemistry in the Markovnikov's rule. So if we were going to add HCl, so 1 equivalent of HCl, we have the nucleophilic pi bond abstracting a hydrogen of the HCl. So now this is where things get a little bit funky, in that this plus charge that remains is now a vinyl carbocation. It's important to understand what that means. The plus charge is actually residing in an sp2 hybridized orbital, not the p orbital, because that's taken up by the pi bond. The conjugate base, Cl minus, then traps that. And so now we've taken 1 pentyne. Let's put in our numbers here, and let's name this 1, 2, 3, 4, 5. So we have 2-chloro-1 pentene. Notice we have no E or Z in this case because these are both H's. So there's no E or Z for this molecule. If we were to treat that with excess HCl, again, Markovnikov's rule is telling us in terms of carbon 1 or 2, carbon 1 has the most hydrogens, so it gets protonated. That generates a secondary carbocation that is then trapped by the chloride. So we end up with the following product. So this is a geminal dichloride. We would call this 2,2-dichloropentane. And again, just to highlight the importance of these reactions, we're taking a hydrocarbon, specifically an alkyne, with 2 degrees of unsaturation, so a relatively nonpolar molecule, treating it with excess HCl, doing a Markovnikov type addition across that triple bond. Now we're installing 2 chlorines at the 2 position, 2 hydrogens at the 1 position. But the presence of these chlorines now adds polarity to this molecule. And again, the functional groups impart properties to the molecule that we as humans use in our civilization to make life as we know it possible. So one final alkyne addition reaction is an oxidation reaction using ozone, which we saw was O3 gas. In this example, so here's our generic alkyne O3 gas. And we're typically going to use an inert solvent such as dichloromethane. And then we're going to follow this up with an aqueous workup. And so what now this does is cleaves the triple bond. So we have a sigma bond, we have 2 pi bonds. That's the triple bond. So it's cleaving that total. Now count 1, 2, 3. Remember the ozonolysis of an alkene where we ended up with a carbonyl? Because we have this 3rd bond, we have to account for that. So all 3 bonds end up to heteroatoms. So the products that result from the ozonolysis of an alkyne are both carboxylic acids. So let's highlight with color as we did before. If this is this carbon, this carbon. Now in terms of the oxidation state, remember we said 1, 2, 3, and we count 1, 2, 3 bonds to heteroatom. So we're now at an oxidation state of 3. And again, this is most useful when R1 and R2 are the same thing so that you're not ending up with different carboxylic acids. So you want to start with a symmetric internal alkyne so you get 2 equivalents of the same carboxylic acid. And again, why is this useful to us? We're taking a nonpolar hydrocarbon. When we treat with ozone, followed by aqueous workup, we're getting a polar functional group out of the molecule. So what if we started with the following? Three hexyne. Let's go ahead and draw that. So I've drawn four carbons. Now I've drawn 6. Let's just throw some numbers in there. 1, 2, 3, 4, 5, 6. So you can see this is a symmetric internal alkyne. So 3 and 4 participate in the triple bond. 2 and 5 are the same. 6 and 1 are the same. So when we treat with ozone, again, we bubble ozone gas into dichloromethane. We watch for the bluish color to show up. We're going to follow that with an aqueous workup. We're going to oxidatively cleave here. So each carbon then ends up with the carboxylic acid functional group. So we've taken 3 hexyne and we've prepared 2 equivalents of propanoic acid. So again, think about spectroscopy when you produce something like this. Obviously, IR, you're going to see this OH stretch, this broad OH stretching. The carbonyl, proton NMR, you would see 1, 2, 3 unique signals. Carbon NMR, you would see 1, 2, 3. You could further differentiate those. You'd have 1 sp2, 2 sp3. So really, really think about all of the stuff you've learned and apply it to this molecule. Again, you have 1, 2, 3 unique type of hydrogen. You have, they're all different pKa's. You have the acid functional group. You have an allylic hydrogen, which is sp bonded to an sp3 hybridized carbon. This one is much more acidic than this one. So this is alkane-like. This is allylic-like, and then this is an acid. So your acidity, this would be the most, the next most, and then the least. So think about all this stuff as a review when you're going through these problems, and try not to just view it as like a one-off. Try to apply everything you've learned just to keep your memory fresh. So sometimes you can see these reactions presented to you as a puzzle. So for example, I'm going to write SM question mark is treated with O3 gas, dichloromethane, then water. And say that you end up with these two different carboxylic acids. And so you really need to be flexible in how you think about solving this. So it's asking you, what is the starting material that when treated under these conditions give these two products? So let's just go ahead and use our color pedagogy here. We're going to use red for that carbonyl, blue for this one. Again, what this is helping us say is that this carbon and that carbon were bonded to each other in a triple bond. If we count, this is 1, 2, 3 oxidation state, 1, 2, 3. So those were bonded to each other by a triple bond. 1, 2, 3, there's our triple bond. Let's put our color in just to help us map. These things don't have color as we perceive them. The color is just there to help us learn and track where these atoms are going. We can then see that the red carbon has this isopropyl group bonded to it. And then the blue carbon has this methyl group. So that would be the starting material that when cleaved under ozonolysis conditions gives those two carboxylic acids. So in this screencast, we've seen a couple different reactions to synthesize internal alkynes from terminal alkynes, then using the concept of retrosynthesis to look at any alkyne and determine two different nucleophile electrophile pairs in which to make that alkyne. We've then looked at some addition reactions in terms of hydrogenation of an alkyne to an alkane, poisoned hydrogenation to form a cis-alkene, dissolving metal reduction to form a trans-alkene, addition of molecular halogens, additions of hydrohalic acids, ozonolysis to give us carboxylic acids. And again, the big picture of this is taking nonpolar functional group alkyne into different functional groups which have added value in physical properties that we use in everyday life.